Okay, so now this is the application, a straight application of the central limit theorem. How does this help us? How does this help us in obtaining a confidence interval? What? Yes?
You can look up known values for confidence intervals for Gaussian.
For what Gaussian?
Well, the standard Gaussian.
Standard Gaussian. So I didn't say that this converges to the standard Gaussian, and actually for most of the random variables, this actually do not converge to the standard Gaussian.
If you find the variance of your distribution, then you can scale these. It's like the relationship between a standard Gaussian and the other Gaussian is just like a zero means scaling.
Right, so we need another transformation, right? So we already have a Gaussian with a zero mean, and any Gaussian is determined by two numbers, mean and variance. So as long as we can find the variance of this Gaussian, we are done. We know exactly what the distribution is. We know exactly at what value of P I have a 95% confidence interval, at what distribution I have 99%, at what distribution I have 99.9%. All right, so this is really just trying to find the variance of this guy. Now the variance of this guy is actually also very simple. The variance of this is actually equal to the variance of each of these IIs. So that's also simply from the fact that all of the IIs are independent and also identically distributed. You can basically go through a bunch of algebra to figure that out, right? So if there is a square root of n inside the variance, you pull it out, it becomes n. If you have a summation of independent terms in the variance, it becomes just the variance, the summation of the variance of these independent terms. So basically, the square root of n cancels with the summation, right? And you get the variance of each II. Okay, so that becomes pretty easy to do. The procedure now becomes the following: you estimate the probability, and then you estimate also the variance of this II, which is what? The variance of II is equal to expectation of II square minus the expectation of II square, right? So that's the definition. I mean, there are two forms of variance. One form is expectation of II minus expectation of II square, right? Another form is this. In this case, this is easier to compute because I know II square is equal to II. And the expectation here is P, small p. This is P square. What I get is P times 1 minus P, exactly what you said. So the conclusion is that not only I know that the square root of n times big P minus small p converges to a Gaussian, I know it converges to a Gaussian of zero mean and a variance equal to that. So, for example, let's try to figure out, for the case we just computed, we repeated the experiment 3 times and we get a variation pretty much in the 4th digit after the decimal point, right? We get a 3, 6, 2, 6, and 2, 9. So let's try to use the central limit theorem to see what we get. So let's just take one of these p's and compute the variance is equal to p times 1 minus p. So this is the variance we get on the square root of n times p minus small p, right? So if that's the variance of the p minus small p scaled by square root of n, what is the variance of just the p minus p? Yeah, right. So when we're talking about variance, the variance is scaled by scales with the square of the random variable, right? So if this is the variance of my estimator is going to be divided by n, or n samples. Okay, so the variance is actually pretty small, 4 times 10 to the 7. But how does the variance tell us the variability in the result? Right. So okay. So a Gaussian, in order for us to actually quantify the confidence, let's actually draw all the potential P's we can get. So this is probability. This is our random variable P. So let's say this is the real P. Okay, we actually get a distribution that is centered at this P with it's Gaussian distribution with a variance of 4 times 10 to the minus 7. So how do we know if I want let's say I want a confidence of 99%, which means the mass within here needs to be 99%. How do I know how wide this interval is? Yeah, so first of all, I need to the variance needs to be transformed into the standard deviation, because the variance actually has a different unit as the quantity we are trying to predict, right? It's a square to the quantity we want to predict. So we always want to square root the variance to get the standard deviation, and the standard deviation is actually 6 times 10 to the 4, or it is actually in the 4th digit. It is 0.00065, right? So that's the standard deviation of the Gaussian STD is about 0.00065. So for the Gaussian distribution, if we know the mean, if we know the standard deviation, we know everything. The number we are going to get when we do the random sampling theoretically it can go all the way from minus infinity to infinity, because it's a Gaussian. But practically, for almost for very high probability, essentially it lies within plus and minus 3 standard deviations. So if you look at 3 standard deviations, the mass within is 99.8%. If you only look into 2 standard deviations, like over here, if you look into 2 standard deviations, you are actually cutting a significant amount of mass outside. So if you only look at 2 standard deviations within this within the green circle, you get 95% of the mass. So depending on how confident you want your result to be, you either choose 2 standard deviations or 3 standard deviations. That's really the confidence interval.